Good evening everyone, I am Varsha. Today I will be presenting round robin scheduling, design and compare. First, the introduction. Round robin is a primitive CPU scheduling algorithm which means a running process can be stopped before it finishes. It is mainly used in time sharing and multi-user operating systems where fairness is very important. Each process gets a fixed amount of CPU time called a time quantum. Once this time is over, the process is printed and moved to the back of the ready queue. This rotation continues until all processes complete execution. The biggest advantage of round robin is that no process starves and all processes get equal CPU chances. However, its performance depends strongly on the selected value. Next, the objectives. The objectives of round robins are to practically implement the round robin algorithm using the C programming language. And next, to calculate and compare important scheduling parameters like waiting time, turnaround time, and response time. Next, to find the optimal time quantum, which gives the best balance between fairness and CPU efficiency. Next, to understand the internal working of round robin scheduling. And finally, to analyze how changing the time quantum affects system performance. Next, we have experimental setup. For experimental setup, we are using the programming language C. Next, the compiler was GCC, and the editors are Visual Studio or Dev C++ or Code Blocks. Next, the OS is Windows 10 or Ubuntu, and the dataset descriptions are for process 1, the arrival time is 0. For all process, the arrival time is 0, and for process 1, the bus time is 10. For process 2, 4. Process 3, 6. Process 4, 8. And we are testing the different quantum values such as 2, 4, 6, 8. These different quantum values help us understand how small and large quantum sizes impact performance. Next, the implementation of the round robin algorithm includes these steps. First, we take input of number of processes along with their arrival time and burst times. Then the burst times are copied into a remaining time array which tracks how much time is left for each process. Next, the time quantum is entered. We use circular queue logic to schedule processes. If a process's remaining time is greater than the quantum, it runs for one quantum and is then moved to the back of the queue. If the remaining time is less than or equal to the quantum, the process finishes and its completion time is recorded. Next, the Gantt chart is drawn after each execution step. This process repeats until all processes are completed. Finally, waiting time, turnaround time, and response times are calculated. Next, the observations. We observed several key performances matrices. Waiting time. The total time of a process waits in the ready queue. Next, the turnaround time. The total time taken from the arrival to completion of a process. Next, the response time, the time between a process's arrival and its first execution. Context switches, the number of times CPU switches from one process to another. These matrices help us compare how efficient the CPU scheduling is for different quantum values. Here the comparison table is there. For the quantum 2, the average waiting time and context switches are very high and average turnaround time is high, response is best. And next for quantum 4, average waiting time and context switches is medium and also turnaround time, response is good. And for similarly it is compared for 6 and 8 quantum values. The key observations we have seen is when the quantum is very small, the response time is fast, but the number of context switches increases, which increases CPU overhead. When the quantum is very large, the algorithm behaves similar to first come first serve, leading to higher waiting time. Therefore, a balanced quantum value is necessary to achieve both fairness and efficiency. Next, we will see the flowchart. This flowchart shows the working of the round robin CPU scheduling algorithm step by step. First, the program starts and we input the number of processes along with their arrival time and burst times. Then, the burst times are copied into a remaining time array to track how many execution time is left for each process. Next, we enter the time quantum, which is the fixed time each process gets on the CPU. The scheduler then picks the first process from the ready queue and checks whether the process has finished. If the process is not finished, it is executed for one time quantum and then placed at the end of the queue. If it is finished, it is removed from the queue. These steps are repeated continuously until all processes are completed. Finally, the algorithm ends and performance values like waiting time and turnaround times are calculated. Finally, the conclusion. From our experiment, we conclude that round robin performance heavily depends on the size of the time quantum. Smaller quantum gives better fairness and faster response, but causes higher CPU overhead. Larger quantum reduces overhead but increases waiting and turn time. The best overall performance was obtained with quantum 6 because it gives low waiting time, low turnaround, fewer context switch, good system responsiveness. So this makes quantum 6 the most balanced choice in our test case. And this helped us gain practical understanding of CPU scheduling concepts like preemption, ready queue, and context switching. Overall, round robin is a simple yet powerful scheduling technique when a properly balanced time quantum is selected. Thank you.